Hey physics students, this is Mr. Galoya coming at you. Hey, let's get into free fall here. So what exactly is free fall? Well, free fall is a type or a special case of an acceleration that's caused solely by the influence of a planet's gravity. And this was researched by Galileo around 1590. And at that point in his life, Galileo was a professor at the University of Pisa. And at least the story goes that he would drop objects off of the Leaning Tower of Pisa and do his experiments and investigations on those different objects and this type of motion. So again, free fall. What is it? It's a special type of an acceleration caused by the sole influence of a planet's gravity field. Now we're not going to include any sort of air resistance. We're going to ignore and neglect the effects of the atmosphere. So the idea was, I guess the old idea was that objects fall differentially based on their weight. And Galileo really proved otherwise. He basically said that all objects accelerate equally. Now, it was later found that this acceleration on our planet Earth, to be negative 9.8 meters per second per second. Again, that's an acceleration unit, right? We have basically a change of a velocity with respect to time. Meters per second per second. And that's the value for our planet's acceleration using the metric system. Often we'll see it in terms of feet in second. We'll see this value that's negative 32, and that corresponds to negative 9.8 in the metric system. But in terms of feet in seconds, it's minus 32 feet per second per second. And often you'll find these problems in math books that they'll use minus 32 feet per second per second. In terms of a physics classroom, though, we're going to be using negative 9.8 meters per second per second. And often this number may be rounded to minus 10 meters per second per second. Now that number is so important really in terms of physics, is we call that, or this acceleration, we call this acceleration the acceleration due to gravity when we have an object in free fall. And we give this idea kind of a special symbol. We call it little g. And it's the special acceleration we have when an object's in free fall. And every planet or moon has its own value for this little g. On our planet, the value we have is minus 9.8 meters per second per second. But that's not true for the other objects in our solar system or universe. The moon's little g, negative 1.6 meters per second per second. Mars, negative 3.8. Jupiter, when I looked this up, I found kind of a range of values for Jupiter. Now, typically we'll call these accelerations negative as the object is falling towards the surface of the planet. Now, it's important for you to understand that an object could be in free fall and be moving downward. So for example, maybe we release an object from rest and it's moving downward towards the surface. However, an object could be in free fall and be moving upward. So maybe I throw a baseball up in the air. Well, it's still really being affected by gravity. So we could have an object be moving upward or downward and be in free fall. Okay, I'm going to include several other videos here, kids. I'm going to drop a couple objects, and I'll show you that they hit virtually at the same time. One of the astronauts did kind of a famous experiment on the moon called the feather and hammer experiment. There's a video of that. I'll include that also. I'll also include a few LogaPro videos. I've got some motion graphs, idealized data to show you on LogaPro, and then I'll actually do a video analysis of a dropped object. And finally, we'll work a few practice problems. We'll talk to you later, kids.
A little bit.
Dave, this is Houston.
Go ahead.
Roger, we're wondering if you could use that to mail home an ounce of rocks, please.
Ounce? All right. I'll do that. I bet we could. And I'll stick this in the ETB. You'll hold your camera right there. I'll be right back. Something else I think you'll find rather interesting. It'll only take a minute. Put this penetrometer drum in the ETB, Dave. Okay. As well as the solar wind.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Okay, so I'm using Logger Pro now to construct some of the three motion graphs for free fall. So what we're saying is basically we're going to drop an object and we're going to have that object then fall to our Earth in a free fall state. So what I've done is I've created a perfect sort of data set here. I've got time 0 to 5 and then this little g. Now that represents an acceleration. Now as long as you're close to the planet, close to our surface, that little g is going to be negative 9.8. And again, that's an acceleration, meters per second per second. So that, if we graph these two columns right here, that's going to be an acceleration time graph. So again, what I'm showing you here then is 4 quadrants. So this is our 4 quadrants, first, second, third, and fourth. So the acceleration time graph is going to be a horizontal line in the 4th quadrant. Again, it should be a little bit shy of negative 10 for our planet. Every planet then has a different than little g, or an acceleration due to gravity. So the acceleration due to gravity is minus 9.8 for our planet. It's negative because it's a vector going downward. Alright, so in terms of the velocity time graph, okay, so let me show you what I did here. This is a calculated column. So we're going to use again that the final velocity is the initial velocity plus the acceleration times time. So that's my expression I have here. And so there's no initial velocity if we're just going to drop an object. So I'm basically dropping an object to the surface. So we'll take our little g, that'll be negative 9.8, and we'll multiply it by the time. So I'm going to click done here. There's my data. So every second, the object would gain a negative 9.8 meters per second worth of velocity. So if I go to my velocity time graph, and let me expand this out just a little bit. Okay, again, we have our 4 quadrants. This would be our 4th quadrant. And we would have a linearity here. Okay, in fact, if we choose the line here, linear fit, that slope then is telling us the acceleration, which again is negative 9.8 meters per second per second. Okay, so we get a diagonal line. Now, if we're on a planet that has more gravity, a bigger acceleration, we would have a bigger inclined slope. So, for example, if we're on the moon has a gravity of around minus 1.6. It's going to be, it's going to have the same shape, but it's going to be less inclined. All right. Finally, then, we have our displacement. How far will the object fall? Okay, so let me show you my equation. Again, we would say then, in the initial position, which is going to be a reference point, that'll be 0, and then VIT, okay, but there's no VI, so this term will go to 0. All we really have then is 1/2 AT squared. So I'm going to take then 1/2 times the little g, my acceleration, and then times the square of time. You can't see the time data, but remember this basically based on the square of time is going to be parabolic. So let me click then the displacement graph. Okay, now it says by the end of the 5th second the object would have traveled 122.5 meters below where it started. That's what that negative sign kind of means there. So let me just type in maybe minus 200. All right. See, there's my parabola right here. So there's my parabolic sort of shape. So these free fall graphs, we see the same types of shapes. Our acceleration time is horizontal. Our velocity time graph is linear, and our displacement time graph is parabolic. But those shapes are going to be, as long as we're dropping an object from rest, those shapes will be kind of in the 4th quadrant. Okay, we'll talk to you later, kids. Bye. So basically in the last video I showed you kind of Logger Pro and how in terms of an object falling, in terms of the ideal sorts of graphs, when we actually do a video analysis with Logger Pro, we get some pretty good looking data and some pretty good looking graphs. So what I did is I had this one video, I think I showed it to you, where I basically dropped 2 objects simultaneously and they hit virtually at the same time. So what I ended up doing was taking these, I guess it's a softball, and dropping that object, and I did a quick little video analysis. So you can see these blue dots here represent kind of a motion map, like a ticker tape, right? And so the object is, every successive time interval, the object is going further and further downward. So when we take that data then and we plot then our displacement time graph, that's kind of what we get here. So this represents then the displacement time, or position, really a position time graph. It's a displacement as a function of time. And so there's our parabola. Again, this is our 4 quadrants, 1st, 2nd, 3rd, and 4th. So we drop that object and it's falling below where it started. So we see then this parabola that's going to look like this in the 4th quadrant. Then when we look at the velocity sort of time graph, and let me get a little more scaling here, we think this should be a linearity. It's not super bad. It doesn't look too bad really, and if I do a sort of a linear fit with that, we know at least on our planet we should get negative 9.8, and you can see I'm within about 10% of that or so. Not too bad. Okay, so this is how, again, the graphs look. This is kind of how the graphs look. Velocity time graph, a linear function. That slope is going to be then little g. Okay, it's going to be then a negative kind of diagonal in the 4th quadrant. And then when we do our position time graph, it's also going to be in the fourth quadrant. It's going to be then, it's going to basically be, well, let me just show it to you. Let's just do the curve fit here. So we think it's quadratic. So I'm going to try the fit. I'm going to click OK. So again, this is half of the acceleration. This graph is telling me the acceleration is around minus 10.2. Again, that's pretty close to negative 9.8. Negative 10.2, pretty close to negative 9.8. And then the full, let me kind of move this out of the way, the full parabola would kind of look like this. So again, this is kind of a it's kind of a bottom opening parabola here, but it's actually, we're seeing just this one lobe of it in the fourth quadrant. Hey physics students, in this last segment of the video I'd like to work a few practice problems with you. And again, these would be free fall problems, and the idea is that we're going to drop an object. That object will be in free fall, and we can look at different aspects of that object's motion, such as how fast is it traveling as a function of time, how far did it travel over some sort of given time, or maybe how much time it took for an object to fall a certain displacement. So why don't we get started? Okay, so I'm working here on my dot camera. So we're basically doing some free fall problems where we're just going to be dropping an object. So what we basically have here then is I've got this object that I'm dropping. It starts from rest, so my initial velocity is 0, and I'm calling this then a reference position or reference point, so my x sub I is 0. So we talked in some of the previous parts of the video about our motion graphs. So we basically have these three types of motion graphs: a position time graph, that's going to be parabolic; our velocity time graph, again we're starting at rest, velocity is 0, and my velocity gets greater and greater negatively as a function of time. My acceleration then will be, acceleration time graph will be a horizontal. And so depending on what planet or what object we're on in the solar system or universe, that acceleration, or that little g, the acceleration due to gravity, will be a unique value. For the Earth, we have negative 9.8 meters per second per second. That's for the Earth. For example, on the Moon then, our horizontal will be then a value that's less than that negative 9.8. It's going to be negative 1.6 meters per second per second. Again, this type of motion is an accelerative motion, and so we have then the unit meters per second for this little g, which is again called the acceleration due to gravity. So we have our same kinematic equations that we've been using earlier in the year. We have our how fast equation, we have our how far equation, and we also have the timeless or combination equation. We had built this equation really by linking these two together and factoring out the time. Often in these free fall problems, we exchange that a for then that little g, and that's telling us really that we're dealing kind of with the free fall problem. Okay, so why don't we kind of get started here. So let's say we allow the object to fall for 3 seconds. That'd be a time, and again we're just dropping that object. Our initial velocity would be 0, and our initial position, x sub I, would also then be 0. We're at a reference point. So let's say we'd like to figure out how far the object is traveling at 3 seconds, or how fast it's traveling at 3 seconds. And we can do then this problem for the Earth, and then we can also do this problem on the Moon, or for the Moon's gravity. So we want to figure out how fast the object's traveling, so we use our how fast equation. V sub f equals v sub I plus gt. Again, we're substituting that acceleration in our equation for the acceleration due to gravity, little g. So on our planet, our little g is negative 9.8 meters per second per second. Again, that's an acceleration unit. We multiply that then by the time, 3 seconds. We get minus 29.4 meters per second. One of my seconds in will cancel out. So on the Earth, at the end of 3 seconds, how fast is that object traveling? Negative 29.4 meters per second. Now this could be any object that's dropped, as long as that object is in free fall, and we're not worrying about any air resistance, etc. And that's the definition really of free fall, solely under the influence of gravity or planet's gravity. If we did this on the moon, we have the same equation, but my acceleration, my little g now is different. It's minus 1.6. So we'll take that value or that number times 3, and we get then that acceleration, negative 4.8. Now again, these are vectors, so we have the magnitude, how big that vector is, or that value is, and then that direction represents a downward idea. So on our velocity time graph, we have a negative diagonal, or negatively inclined diagonal. We start at rest, and that object gets faster and faster. On the Earth, it would get faster by 9.8 meters per second per second. It would increase its speed by that much. On the moon, because the gravity is less, we're only going to see we would see a smaller increase. On the moon, we'd have the same type of graph, but our diagonal would be less inclined. Okay, so we figured out how fast the object is traveling at 3 seconds. Now we can also figure out then how far it would travel in a given amount of time. So let's use again the same time unit, 3 seconds. Again, now we're going to be using our how far equation. Now we know then that when we look at position as a function of time, we're going to be seeing parabolic sort of shape on our position time graph. That's because we have a square of time here in our equation. Because we're dropping the object from a reference point with no initial velocity, these two terms will factor out. Okay, we don't have to worry about those two terms. We have 1/2 times the acceleration. Again, that acceleration on the Earth is negative 9.8. And then we basically take and multiply that by the square of time. So on the Earth, in 3 seconds, the object would be 44.1 meters below where it started. Where would it be on the moon? Well, again, we'll have to use the acceleration due to gravity for the moon. That would be 1.6. So on the moon, we multiply everything through, we get 7.2 meters below where it started. Check your units here. We're going to square our seconds, and that'll cancel out with the seconds here, and we're left in with meters. Okay, well, let's just look at one more type of problem that you might see. In this case, let's say we're dropping the object from maybe some high cliff or so, and we know then how far that object will travel in free fall. We'd like to then solve for time, like how much time would it take to fall a certain distance or displacement below where it started. So we can again do this for the Earth, we can do it for the moon, and we're going to be using again our how far equation, and in this case then our x sub f would be our 100 meters, but since we're falling below where we started, we're going to put in then minus 100 meters. X sub I again would be 0, bit again would be 0, and we're left in with 1/2 times the negative 9.8 meters per second, and we're going to solve this again for t, for this type of problem. So we want to get and solve that for time. So we have a negative sign here and a negative sign there, and those will cancel. So we're left with 100 times 2. We're going to divide that by 9.8, and then remember to take a square root. So the time it would take for that object to fall 100 meters would be around 4.52 seconds. Now notice your units. We have meters here. We're going to divide it by meters per second per second. So we have meters divide it by meters per second. The meters cancel. This is really seconds squared. That'll kind of come up to the numerator. We'll take a square root of those seconds squared, and we end up then with seconds. That would be how much time it would take for that object to fall on the Earth. We can also do the same thing for the moon. We'll use the moon's gravity. Okay, we've got then 100 meters times 2. Divide that by 1.6, and then take a square root. We get around 11.18. 11.2 or so, 11.18 seconds. Okay, so the object on the moon is going to take much longer to fall that same displacement because the gravity again is much less. So there are three types of problems that you might see that are sort of basic types of problems. Again, in this first video set of problems, we're just dropping an object from rest. Okay, and we want to look at its motion below where it started. We can solve for how fast the object is traveling. We can solve for how far it will travel given a certain amount of time. Or if we know then how far it fell, we can figure out how much time it took. Talk to you later, kids. Bye.